Alright, welcome to lesson 5.06. We're going to continue with related rate problems, and we're going to look at some situations that involve volume and surface area. So to begin with, it's good to remind ourselves of the key characteristics of a related rates problem. So go through and answer question 1, then go on to 2 and 3. If you're having trouble remembering the key characteristics of a related rates problem, you might go back and review the last lesson. And if you are thinking about number 1 and still stuck, go ahead and check what I say about it before moving on to 2 and 3. Alright, there are two, I think, key characteristics about related rates problems that come to mind. The first is that the variables we're dealing with depend on time. We're dealing with rates, and rates need a time component. So we're going to look at a situation where a bunch of things are depending upon time, things are changing over time. That's going to be a related rates problem. The second thing is that there is a relationship between the rates, meaning that I can write an equation relating to variables, and then when I take the derivative of that equation, I'll have an equation where there's a relationship between those particular rates. So those are the two key characteristics that I'm looking for. Now for 2 and 3. So for 2, I assume the radius r of a sphere is a differentiable function of time. It's a key that this is a related rates problem. And let V be the volume of the sphere. Write an equation that relates dV dt and dr dt. Alright, so the first thing that I need to do is write an equation that relates r and V. And then when I take the derivative with respect to t, I'll have an equation that represents the relationship between their rates. It is important to note that since the volume of a sphere depends on the radius, and the radius depends on time, that the volume itself actually depends on time as well. So it's a key thing to take note of, that both variables that we're dealing with depend on time. So if you don't recall, you could go Google or look in the back of your book. There should be a place where they have a bunch of equations that you might need to use, and the formula for the volume of a sphere is one of them. So go ahead and check that out and use the volume of a sphere formula to work through number 2. And then for number 3, you can do the same thing with the volume of a cone, and we'll take a look at those relationships in a second. Alright, so for number 2, the volume of a sphere is given by 4/3 pi r cubed. Now I can take the derivative with respect to t on both sides of my equation, and I'll have a relationship that involves dV dt and dr dt. Alright, so taking the derivative with respect to t on both sides, notice that 4/3 pi is a constant, so I can factor this out. And now I'm just taking the derivative of r cubed. Remember, r is a function of t itself, so I'm using the chain rule here, differentiating implicitly with respect to t. So this is going to be the derivative of the outside, which is 3r squared, times the derivative of the inside, which is dr dt. And then I just have 3 over 3, and that'll be equal to 1. So I'm left with 4 pi r squared dr dt. Taking a look over here, the formula for the volume of a cone is pi over 3 r squared h. And when differentiating here, notice that both r and h are functions of t. So while I can factor out this constant, I will need to use the product rule to take the derivative of r squared times h. Alright, so factoring out pi over 3 here, the derivative of r squared times h. So using the product rule, I'm going to first have r squared times the derivative of h with respect to t. So it'll be r squared dh dt plus, and now I have the derivative of r squared. Now this is a function of t itself, so it'll be the derivative of the outside, which will be 2r, times the derivative of r with respect to t, 2r dr dt times h. And I might just rewrite the h variable before the rate of change. That's just a convention. So the derivative of volume with respect to t would be pi over 3 times r squared dh dt plus 2rh times dr dt. So notice what we've done is we have used some pretty basic formulas that represent the volume of a sphere and a cone at particular points. So this is these are both static functions, meaning that I find some particular r radius, and this formula gives me the volume for that particular radius. But because we are able to differentiate, we can find, using this formula, a relationship that actually represents a relationship between the rates at which r is changing over time and the rate at which volume is changing over time. And so using that, we can then solve for the rate at which one of them is changing if we know the rate at which the other one is changing. And the same here. That's a very powerful skill, and one that we will make good use of going forward. All right, I just wanted to have a quick reminder of the strategy that we're going to use when solving related rates problems. Obviously, understanding the problem is such a key component. Make sure that you identify the variable whose rate of change you are seeking, and the variable, or maybe there's multiple, whose rates of change you know. You need to write those down so that you can figure out what your equation should look like, what variables need to be included in your equation. And you want to develop a mathematical model, meaning you need to draw a picture. These are going to be geometric shapes, drawing a picture, and labeling is going to be incredibly important. I sometimes do 1 and 2 interchangeably. The reason that I sometimes do that is having a picture of the problem first can sometimes help me make sure that the variable whose rate of change I seek and the variable whose rate of change I know are in the right place. It's also incredibly important not to label any quantities that change over time. So you'll be told, find this rate of change when r is 3. Well, that doesn't mean r is always 3. That means that at that particular instant, r is 3. So you need to make sure that you're only labeling things that are constant if they really aren't going to change at all during the process. Incredibly important. Obviously, writing the equation is the crux of the whole problem, and steps 1 and 2 are going to make sure that you write that equation correctly. Your equation, of course, should relate the variables whose rate of change you seek with the ones that you know, because then when you differentiate, you'll have an equation that relates both of those rates of change. And of course, that's step 4. Make sure to remember all of your rules and differentiate with respect to t, so you're differentiating implicitly. Once you've then found an equation that relates the rates, then you can substitute any quantities that depend on time. So when it says when the radius is equal to 3, well, that only happens at that exact instant. So you're only substituting in that value after you've differentiated. And then you want to make sure you interpret your solution with correct units and describing whatever it is that you need to describe. So don't forget, you should have all of these pieces. I, in fact, label them, steps 1, 2, 3, 4, and 5, either on my paper or in my head, and you should too. All right, let's go ahead and take a look at a couple of problems. Okay, so let's start with a common problem in related rates. You have a spherical balloon. Anyone that's seen a balloon knows they're not perfect spheres, but we live in this nice world here in AP Calculus where they exist. A spherical balloon is being inflated at a constant rate of 2 cubic meters per minute. Find the rate at which the radius is increasing at the moment when the radius is 3 meters. I want to encourage you to try this on your own first, and I recommend just following steps 1 and 2, trying to get those done. And if you feel successful with that, moving on and trying to complete the whole problem. If not, take a look at the, go ahead and press play, and we'll go through the first couple of steps, and then you can pause and move on from there. Okay, so step one is easy enough. I think the trickiest part is recognizing the first piece of information they give you, which is that the spherical balloon is inflated at a constant rate of 2 cubic meters per minute. This is a volume, and you can tell that because of the cubic dimension here. 2 cubic meters means you're dealing with a volume. And so this is a constant rate. So dV dt, the rate at which the volume is increasing with respect to time, is always 2 cubic meters per minute. So that's the rate that you know, and you want to find the rate at which the radius is increasing. You want to find dr dt, and it's at the moment when the radius is 3 meters. So now we are going to go ahead and draw a picture of the sphere and label the important pieces. All right, so here's my poor attempt at a spherical balloon. If you didn't make the balloon opening and the reference to the volume going in, that's okay. The key is that we have a sphere, so I draw a circle and then kind of this half circle in the front with a dotted circle in the back. Represent the radius there is r. It's important that you represent it as r and not 3. This is something that's changing, obviously. We're trying to find the rate of change. And so only once we've found our equation that relates the rates do we want to actually evaluate at this moment in time when r equals 3 meters. So now I can go ahead and write an equation that relates r and v. Those are the rates. The rate that I know is the rate at which the volume changes, and the rate that I want to find is the rate at which the radius changes. So if I have an equation that relates the two variables, then when I differentiate implicitly, I'll have a relationship between the two rates, and I can solve for dr dt. If you haven't worked through the problem already, make sure that you have steps 1 and 2 down and try and complete the problem now on your own, and then we'll take a look at the solution. Okay, so you can look this up. The volume for a sphere is 4/3 pi r cubed. On most tests, they're going to give you any equations that you might not have memorized, but this is a good one to have a pretty good idea of here, just in case. So now that I have this relationship between v and r, I need to differentiate with respect to t so that I have a relationship between dr dt and dv dt. So just as we did in the discovery problem, I'm going to take the derivative with respect to t of both sides of my equation. Notice that each of the variables, of course, is a function of time because r depends on time and v depends on r. They're all implicitly functions of time. So the derivative of v with respect to t is just dv dt. And here I can factor out a 4/3 pi, and I take the derivative of r cubed with respect to time. And as we talked about in the discovery problem, that's going to be 3r squared dr dt. And the 3's will cancel, and I'm left with 4 pi r squared dr dt. So now I can substitute any values that depend on time, and at this particular instant in time, r is equal to 3, and dv dt is actually constant. It's always 2. So we know that we can plug in 2 here for dv dt. And we can plug in 3 for r. And now we're going to solve for dr dt. So substituting in and solving, I end up with dr dt being equal to 1/18 pi. So this is the rate at which the radius is changing with respect to time. And now I've got to make sure I've got my units correct. I know that the radius is being measured in meters and that time is being measured in minutes. So this is going to be meters per minute. And now I want to make sure I write my answer out, and so I'm finding the rate at which the radius is increasing at the moment when r is 3. So I would say, at the moment in question, the radius is increasing at a rate of 1/18 pi meters per minute. Of course, you could approximate 1/18 pi, but it's perfectly acceptable to write it as in this exact form, because anytime you approximate pi, you'll get an approximation, obviously. So clearly this is a very small rate of change. The radius isn't increasing by a whole lot, but that sort of makes sense because the volume isn't increasing by a whole lot either. All right, let's go ahead and take a look at a problem involving a cone. I might be wrong, but my belief is that the College Board has a favorite geometric shape, and that shape is a cone. This also happens to be my favorite geometric shape as well because you can put ice cream in it. So while we're not going to be putting ice cream in this particular cone, this is a very good problem to understand. So water runs into a conical, meaning cone-shaped tank at a rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? Go ahead and copy the problem down and go through parts 1 and 2, steps 1 and 2 on your own. And if you feel confident about them, I encourage you to then try and move through the rest of the problem and complete your solution. If you are really struggling with parts 1 and 2, then go ahead and take a look at it with me and then move on and complete the solution on your own. It's important to feel okay with struggling at first. These problems can be tough, and only once you've really fallen flat on your face will you truly be able to understand the intricacies of this situation. Okay, there's a lot going on in this situation, but if we break it down and take it one step at a time, it won't seem that unwieldy. First thing I'm told is that water runs into the conical tank, and this is a volume, so this is telling me the rate at which the volume of the water is changing. So I know that my given rate is dV dt, and that is 9 feet cubed per minute. I also know that the height and base radius of the cone or the tank that the water is going into. And my question is, how fast is the water level rising when the water is 6 feet deep? So a couple things here. I wouldn't be opposed to drawing the picture first before I really hunker down on what rate I'm going to be finding. But if I think about the rising of the water, so I'm thinking about the vertical component of the cone-shaped water, that is going to be the height of the cone. And so I do know that what I am going to be searching for is dH dt. I know dV dt, and I know that I want to find this particular rate when H equals 6. Okay? So now let's go ahead and build our diagram. Okay, so here is my tank. Now I think the problem that a lot of people run into is differentiating between the size of the tank and the fact that I don't actually care about the tank. The tank always stays the same. What I'm really curious about is the water that's going into the tank and how that is changing. Notice that when the water pours in, it's going to be in a cone shape. I just know that the cone shape is increasing in size because water is being poured in. So what I'm really curious about are the dimensions of the cone, and that's what of the water in a cone shape. And so I need to represent that in my diagram. Okay, so here is the cone-shaped water inside the tank. And of course, this is what I'm curious about. I want to know how the height of this cone-shaped water is changing. So I obviously need to label the height, and I also need to label the radius because that's another dimensional component of my water. So here is a completed picture of my cone. I have all the variables that I'm going to be dealing with here. And there's one more thing that is important to recognize, and we'll see why this is so important in a second. Imagine that I had drawn the height actually inside both of the cones. And now consider for the conical tank that I have a right triangle being constructed with the two legs being the radius and the height, and here's the hypotenuse. And inside this larger triangle is a smaller triangle that is relating with bases that are the radius and the height of the cone of water. And so if I redraw this outside of my cone, I have a triangle with another triangle embedded in it. And these are what's called similar triangles, meaning the ratio between their sides are the same. So here I've drawn this taken out of the cone, and you can see that the side lengths, the two smaller side lengths of the smaller cone are R and H, and the two smaller side lengths of the larger cone of the tank are 5 and 10, which tells me that the ratio between 5 and 10 is going to be the same ratio or is equal to the ratio between the radius and the height here of my cone of water. So this is going to be a key relationship that is going to help me in a few minutes. So now with this in mind, let's go ahead and build ourselves an equation which relates the height to the volume of my cone of water. All right, so here is the volume of a cone. The volume of a cone is 1/3 pi r squared h. And notice that I'm representing the volume of my cone of water. The volume of my tank never changes. What's actually changing, of course, is the water, because water is being poured into the tank. And so here I want to make sure that I'm still thinking about the cone of water. Now, my goal was to write a relationship between the volume and the height, right? Because those are the rates of change that I want to find and that I know. But my equation here includes the radius. So we have a couple of options. I could go through and differentiate implicitly, and then I'm going to realize that I have dr dt and the radius involved as well. So before doing that, it would be great if I could rewrite my equation so it was v in terms of only h. In other words, I only had one variable, h, the one that I care about, because when I differentiate implicitly, I'll have dh dt. So we need to look for a relationship between r and h so that we can write r in terms of h. That's where these similar triangles come in. Since these triangles are similar because they are embedded within one another, the corresponding sides have the same ratio, meaning that the ratio between 5 and 10 and the ratio between r and h, since those are the corresponding sides of the similar triangles, are equal. So 5 divided by 10 is equal to r divided by h, which means that I can solve for r in terms of h. In other words, by multiplying by h on both sides, and noting that 5/10 is 1/2, I will find that r is equal to 1/2 times h, or to shorten it, h/2. So with this key piece of information, that r is equal to h/2, I can rewrite my volume equation so that it is volume in terms of height. So I've substituted in h/2 for r, and now I can do a bunch of simplifying. h/2 squared is going to be h²/4, so I'm going to have 1/3 times 1/4, which is going to be 1/12. I'm going to have pi times 1/12, so my constant term is going to be pi/12, and then I'm going to have h² times h, which is h³, so I can rewrite my volume equation very simply as pi/12 times h³. And this is incredibly helpful because now when I differentiate both sides implicitly with respect to t, I'll have a relationship between dv dt and dh dt, and I won't have any other variables to deal with. All right, so differentiating implicitly now on both sides with respect to t, I have the derivative with respect to t of velocity, which is, of course, the derivative of velocity with respect to time, dv dt. Here I'm going to factor out the constant, pi/12, and then take the derivative of h³ with respect to t. Remember, h is a function of time, so I'm using the chain rule, 3h² times the derivative of the inside, which is dh dt. I'm simplifying a little bit. 3/12 is 4, so I'll have pi/4 h² dh dt. Now notice that I have all the values I need. I know that the derivative of velocity with respect to time is 9, and I know that the value of h at this particular instant that is in question is 6, so I can solve for dh dt. All right, so substituting in the appropriate values, dv dt is 9, h at this particular instant is 6. I can solve for dh dt. 6² 36. 36 divided by 4 is 9. I have 9 equals 9 pi dh dt. Divide by 9 pi on both sides, and I have dh dt is equal to 1/pi. Now I want to interpret this correctly. Of course, this is the rate of change of the height, which is going to be measured in feet, and time in minutes. So this is going to be 1/pi feet per minute. And we obviously have an idea that pi is around 3, so this is around 1/3. It's going to be a little less than 1/3. We can approximate if we'd like, giving us approximately 0.32 feet per minute. You now want to go ahead and write out your answer. Make sure that it makes sense and that you're using correct language. But to say it quite briefly, at the instant in question, the height of the cone of water is changing at a rate of approximately 0.32 feet per minute. All right, at this point, go ahead and complete homework 5.06. And don't forget that there is a quiz tomorrow.